Hello and welcome to this segment of Introduction to Autonomous Systems. If you recall, in the last session we had started our discussion on the knowledge base, and as a consequence of that we also introduced the idea of propositional logic as one of the representational languages that one can use to certify the truth or falsity of any sentence which is constructed as per the syntax of propositional logic. Let us now take this idea forward and have some understanding of what might be a logical agent. So, let us begin this segment. So, the concept of logical agent is based on the methodologies and principles of propositional logic, as we have seen, which are expected to help the agent in deducing the state of the world through percepts. So, this is the fundamental idea, that through percepts you construct a statement about the status of the real world outside, and then you verify using the knowledge base the truth or falsity of that sentence, and once that is verified, it is part of your knowledge base, based on which then you do an inference process and come up with a conclusion. And to do that, we need to write down a complete logical model of the effect of its action. Of course, in addition, the agent also needs to keep track of the world efficiently without going every time to the percept history for inference, and use it to construct plans for achieving its goal, because if it has to keep going back to the percept history, then obviously it will be an inefficient design. So, the idea essentially is that once the agent starts working, it keeps the information about the world available to it all the time, so that the moment a percept is received, it already has the information to compare it with, and then it can construct a plan and achieve its goals. And to do that, we can now talk about configuration of a logical agent. So, in order to achieve a desired logical agent, as you have realized earlier, we need to create a knowledge base, and along with it an inference process or an algorithm which is going to search for a particular conclusion based on the percept which has been received. And as we have seen in the last segment, this algorithm should be not only sound, but it should also be complete. Let us assume for the time being that both these are feasible. Now, we bring in some ideas of the effort involved, and to understand the implication of that effort in terms of feasibility of putting such a algorithm in place. So, it is worth noting here that if there are n symbols as part of your logical statement, and you know the symbols as we have defined, nothing but each of them are statements which are connected through logical connectives. So, let us assume that there are n such symbols which are connected to each other, creating sentences which are syntactically correct, and for these n symbols, the total number of models that we will need to check will be 2 to the power n. So, for example, if you have two symbols P and Q, as you recall the table that we had looked at in the last segment, there were 4 options of P and Q. So, obviously, as your number of symbols start increasing, your order of the models will start increasing. So, for example, if you have 5 symbols, you will have 32 models to check, next 64, 128, and it will keep on going like that. And it is found that in the process, while the space complexity is of the order of n, the number of symbols, the time complexity, because you have to check that many models which are 2 to the power n, the time complexity is also of the order of 2 to the power n. However, the propositional logic entailment is of the NP complete type. We find that irrespective of the algorithm that you use for finding out the inference, there will always be a worst case in which the time order will increase exponentially, which means that at some point the amount of time that it will take for you to search a solution will become untenable or practically infeasible. So, in order to address such situations where when we have real life problems, there are obviously likely to be larger number of symbols, and at some point the issue of time complexity will arise, which will have to be addressed. And it has been found that at least to some extent we can employ what we call a propositional theorem to check for entailment instead of consulting the applicable models. You recall, we said that in case we want to have an inference, we have to keep searching for that statement through all the models or verify all the models against the hypothesis. What this propositional theorem says is that instead of doing that, you can check only for entailment, and hopefully with that you will come up with the right conclusion. This is particularly useful when the proof of theorem is shorter than the number of models to be checked. What it means is that as your number of variables or the symbols start going up, your number of models will start increasing significantly, and if the proof of theorem does not increase in the same proportion, then it makes sense to use the theorem rather than model checking procedure. But then there is a flip side to this also, because the theorem proving strategy will require additional steps such as logical equivalence, validity and satisfiability, including use of contradictions or refutations. So, which means you have to bring in all these ideas so that you can prove a particular theorem or a hypothesis, based on which then you can directly do the entailment and without the need for checking models. But with all this, let us now take an overall view of the whole process of logical reasoning itself. We have started with our basic idea that the knowledge base, if it contains logical statements, then we need to use the concept of logical reasoning to arrive at our conclusion and actions. At some point, it will start hitting a different limit, that is not only the number of statements to be checked, a number of models to be checked will be 2 to the power n, which will also mean that your time complexity will become simply huge. There are going to be other issues which are also going to come in, which we will need to look at. In order to do that, let us take a step back and see when this whole process started. The AI related work started in early 60s and 70s, and logical reasoning had been in existence at that time, which means the logical reasoning was already there when AI related work started in 1960s and 70s. But of course, as artificial neural networks or ANNs matured during the 80s, the logical reasoning lost a bit of ground. So, during 60s and 70s, logical reasoning was the main algorithm that was being used to design agents based on artificial intelligence principles. However, people had already realized even before the artificial neural networks came that there were enough practical cases even prior to ANN taking over, which showed that logic alone would not be sufficient because uncertain reasoning was key feature of the problem. The implication of this was that in the real world there was nothing deterministic or black and white like 0 or 1, like true or false, only two states. There was sufficient uncertainty in many things in the real world to make such decisions based on only true or false a little less than perfect and desirable. And that brought in the idea of Bayesian reasoning, which essentially aims to evolve concepts and techniques to arrive at conclusions where the knowledge is subjective and hence uncertain. So, you can clearly see the difference between the logical reasoning where the knowledge was considered to be objective, either true or false, whereas in most cases the knowledge was hazy. You could not say whether it was true or you could not say whether it was false. So, you had to fall back upon something else which was mostly subjective and then still arrive at conclusions which were workable and useful in a context which was reasonably uncertain. So, this brought in an important discipline in the development of AI related systems, that can you reason under uncertainty. But of course, here we have to accept the fact that if the system is deterministic, hypothetically, then the reasoning driven by logical inference process will result in a deterministic conclusion that can be used to decide action. But once you accept the idea that scenario is not deterministic or uncertain, and many times as we have seen from our task environment that it might only be partially observable, unknown, so many things will come into the picture, you can immediately see that deterministic approach is not going to be a viable option. So, that brings us to an important step that we need to understand and take further, and that step corresponds to representing the uncertainty, as to how we are going to capture uncertainty, perhaps quantify it, and then based on that uncertainty still take a decision. And to do that, first let us look at the uncertainty itself, which is found to be a complex phenomenon, which is not really amenable to a generic mathematical description, and there are only approximate models that aim to capture its essential features. In this regard, basic concepts of probability and statistics are employed to generate mathematical models with which we can reason and arrive at acceptable conclusions and decisions. So, this is the primary input that now we are going to need in order to handle an uncertain world, that is, we are going to bring in the idea of probability and statistical tools, based on which we will now create mathematical models with which we can work. We can arrive at a conclusion using the reasoning process, which is now uncertain, and come up with now acceptable conclusions which are probably not from a deterministic process, but a process which is non-deterministic. Of course, this also leads to situations where we need to work with incomplete evidence, and that is something which is going to cause lot of issues to us, which we will need to correctly understand and also assess the value of the conclusion and the decision that we have arrived at, because beliefs is what is going to be what we will have to work with, because we do not have complete knowledge. So, we only believe something to be true or false. We do not know for certain whether it is true or false, we only believe it, and that belief now has to be quantified. And please note that belief falls short of knowledge, it is not knowledge, and you still have to make that belief part of your knowledge base, because that is your starting point for arriving at a strategy to search for a decision, and you can immediately see the possibility that you might have faulty or fallible conclusions, conclusions which may not be correct in many contexts. They may be wrong conclusions, they may be inadequate, so many things could go wrong with these, but then you have no choice. Let us first look at the types of scenarios that we have in uncertainty. Broadly speaking, there are three kinds of uncertainty instances that we need to deal with while synthesizing autonomous intelligent AI based agents. The first is our ignorance, limits of our knowledge that leads to uncertainty about many things. For example, there is only so much that we know, but the problem that you are trying to solve may fall in the domain which is beyond your knowledge. So, there is now an uncertainty about many things that come into the solution of the problem. So, this is the first uncertainty that we need to deal with. The second aspect is that even if we know everything, there will always be a residual uncertainty about the correctness or the exactness of our knowledge, because ultimately it is purely statistical. Our knowledge is never 100%. There will always be a certain residual uncertainty about the correctness or exactness of our knowledge. So, to give you an example, no matter how much we are able to know about the process of spinning a coin, which we know is an uncertain process, we can never say whether we will get heads or tails, and hence accept practical indeterminism that it could either be head or tail, simple, which means you can model everything about the mechanics of a spinning coin. You can model the surface on which it is falling. You can do a very detailed analysis, but at no point you will come with a definiteness to say that when I do the next spin, you will get heads. No, you may still get tails. And the third thing, which is perhaps a property of all humans, is an element of vagueness in most of our premises. See, many times we make statements or we think what we know is based on a premise which perhaps is not very clear. There is some element of vagueness in that. Just to give you an idea, we are not sure if a human should be classified as brave or coward, because that would depend on the context. In some context, the same person could be brave, in some other context, the person could be a coward. And if you are going to base your decision on one of these attributes, chances are you may come up with a faulty conclusion. Similarly, how do you know that thought of a human being is knowledge or is just an opinion? Which means opinion may have some very loose basis, but the thought or opinion may not be knowledge. So, whether a thought is a knowledge or an opinion itself is uncertain. So, you realize that this vagueness is going to trouble us quite a lot. So, ultimately we come to this point that we have to accept the inevitable, that we have to reason with probabilistic knowledge, and that is also the basis for Bayesian reasoning process. So, you realize that without the Bayesian reasoning, which we will talk about in a little while, there is no way we can actually take at least acceptable decisions and come to the conclusions from a scenario which is containing all these three kinds of uncertainties. So, let us look at from where this Bayesian reasoning itself has arisen. The Bayesianism is a philosophy for representing a human trait of subjectivism in all that is said through a mathematical process that can lead to quantitative basis for reasoning process. Now you see the value that this Bayesian reasoning brings in. It says that subjectivism is a human trait, but I am going to use that subjectivism put in a mathematical process which there is some basis that it is workable, from which I can come up with a quantitative basis for arriving at a conclusion. And to do that, while we do that a little later, our first step will be to understand the basic mathematical tool which is going to be used to convert the subjectivism to a number, and that is your probability calculus, which is the mathematical tool for representing appropriate strength of the beliefs, which means if you believe something, how strong is your belief? 20%, 50%, 90%, and that will what will decide what is going to be the actual quantity based on which you will decide the conclusion. In addition, we need to consider the issue of physical randomness and probabilistic account of causality, which means the cause effect relations itself are probabilistic or uncertain. So, if you think that a particular cause is the reason for the effect that you are seeing, it is not definite, and based on that if you reason out a decision and an action, there are likely to be issues. So, you need to bring that also into your whole process of coming up with an overall methodology of reasoning in an uncertain context. So, what are the various aspects of Bayesian reasoning that we should be looking at? So, one of the first application of Bayesian reasoning was in 1960 for the problem of medical diagnosis, in which a set of symptoms did not logically point to a specific disease. In fact, in many cases of course they did that, in which case there was no issue of medical diagnosis being uncertain, but there were also many cases where the diagnosis became an issue because the symptoms did not logically point to a specific disease because there was some kind of internal contradiction in the symptoms. The researchers then developed simple probabilistic relations and implemented a strategy for updating the probabilities in which it was assumed that symptoms were independent, which means they did not have any dependence among itself. We will come to this point a little later with some greater emphasis, but at this point let us just assume that this independence was justifiable. Of course, people also realized, particularly who were medical practitioners, that the above condition of independence of symptoms required them to be of an extreme nature, and hence the tool was really not of much use, because by the time extreme symptoms came up, there was, even though you could diagnose it correctly, it had gone beyond the treatment stage. So, it kind of was an academic exercise at that stage. In 70s and 80s of course, this idea was taken a little further using the same idea of uncertain reasoning and application of Bayesian process, and MySyn, a medical diagnostic tool, was developed in the form of an expert system in which uncertainty was represented as certainty factors. These were based on the opinion of experts in the form of degree of increased belief, which some evidence E implied for a hypothesis H, and it was mathematically represented saying that MB as a function of H, that is hypothesis, and E, which is evidence, belongs to an interval 0 and 1, which means it will lie somewhere between 0 and 1, degree of belief. Similarly, they also came up with another metric, what they call degree of increased disbelief, and which was formulated as the same MD, again function of hypothesis H and the evidence E belonging to the same interval 0, 1. So, this is how the first step was taken in this direction, and then they proposed a mathematical formula for coming up with what is called a certainty factor from these two definitions in the following manner. So, it said that a certainty factor, which is a function of the hypothesis and the evidence, which means how certain is that hypothesis being true, was nothing but measure of belief minus the measure of disbelief, and they said that this will belong to an interval -1 to +1, which means this number could now lie anywhere between -1 and +1. Simple arithmetic that if MB is 0 and MD is 1, it would be -1, and if MB is 1 and MD is 0, it will become +1. So, the complete reach of this certainty factor was -1 to +1. Of course, from the above definition, at least at the very simple level, we can see that changes in MB and MD cause changes to CFs that can be employed for reasoning out the diagnosis in an uncertain context. The implication is that if you have an evidence E for which you now have a belief and you have a disbelief, then based on that you can come up with a certainty factor. So, if this you say that the based on some evidence that you have received, you say that my measure of belief is 0.85 and measure of disbelief is, let us say, 0.1, then the difference is 0.75, and you say okay, the certainty factor for this evidence is 0.75, and that probably is good enough for me to take a call on some treatment line. To conclude this part at this stage, I say that agents based on propositional logic will have or have limited utility in the real world context, mainly because real world is not deterministic, which the propositional logic assumes, and in the context of uncertain reasoning, the Bayesian approach is useful, but we need to understand the probability calculus a little more in order to understand the implication of the measure of belief and the measure of disbelief contributing to your definition of certainty factors, which ultimately will be used for coming up with a conclusion or a decision. So, with that we come to the end of this segment. In the next segment we will continue with this idea of uncertain reasoning, and we will also look at some basic let us say vocabulary and tools of probability calculus, so that we can come up with the quantitative estimates of MB and MD, which will then be used for our Bayesian reasoning. So, bye for now. Thank you for attention and see you in the next segment.